Okay.
Hello everyone on the video on YouTube. Welcome to Organic Chemistry of Chemistry Olympiad at Lambert High School. We're very happy to be with you today. Uh, but yeah, if you get a degree in biology, I don't know how useful that is though if you're not like trying to be a doctor, but
Yeah, that's why I mean the second fastest I could do is math, which is in my opinion more I could do like a math. I'm really close to a Chinese minor. I'm really close to an econ minor. I'm really close to um I'm really close to a chem minor, and I'm also really close to a bio minor.
dude, go for it. Get every minor possible.
Dude, I could literally get every single minor. And then yeah, if I do CS, I'd be really close to a CS minor too. I can literally have like five minors.
Is that useful though? Just have an assortment of minors. Like a minor in China.
I mean,
Imagine having
I
a
have
minor
no
in
idea.
Chinese, economics, and bio.
Okay, I think minors matter if you're like if you want to directly go into industry right after you finish college. But I kind of want to go to grad school, so I really don't know how useful. Like, if I was to apply to a bioinformatics graduate, I don't know how useful like a Chinese minor would be. So
Yeah, that'd be funny. Oh shoot, I'm not sharing my screen, am I?
also, I just checked the average of the final for linear algebra last year was a 77.
Really? I don't know. Yeah, I don't know. There's people that really struggle in their algebra. I don't know. I found it to be pretty easy class. Although like I barely learned. I don't know. I focused on like the first two units. I really knew my crap. And even or yeah, the first two midterms, and I guess like part of the third midterm. But like after the third midterm, like I don't know, I kind of winged it. Because I already did fine enough in the first two.
Well, I mean, I just thought everything afterwards, like the eigenvalues, eigenvector stuff, was like really easy. I thought the third unit was really easy compared with the, I thought the second unit was honestly the hardest.
I did bad on my third, or I did badish on my third midterm, but like that was mostly like just stupid mistakes. Like I knew my crap, I just messed up on the test, but either way, my grade was fine. But multivariable calculus should be harder, right?
I think it depends on the person, but yeah, definitely. And I thought multivariable calculus was harder. Even though I did better in multivariable, it was definitely harder. Also, the thing is, I don't actually don't remember anything from multivariable calculus. I think multivariable calculus is like a pretty useless class. I've used linear algebra so much more than multivariable
Yeah, linear
calculus.
algebra is dope, dude. I've seen it even like I was looking at this thing about Minecraft and linear algebra came up. I was like, yo, I
Yeah,
actually
have you
gotta.
guys done the Google
Yeah,
PageRank
Google
thing?
PageRank. I was like, that's pretty cool.
Pretty,
It's pretty interesting. No, with linear algebra, it was you know like basically the way like the world generates in Minecraft is like some not super complicated, but like some math that can be sort of modeled with linear algebra. Like if you're trying to like solve for specific things. So it's pretty interesting.
yeah.
Oh, by the way, welcome everyone to organic chemistry. Although right now we're talking about other random crap. Yeah, we'll get started soon. We're finishing up sort of the thing about organic chemistry. So uh, the previous one we kind of talked about foundations of organic chemistry, I would say, like talking about naming, um, isomers. I mean, naming is like so you can even be able to understand the basic stuff. Now we're going to be sort of talking about, I guess, things that you'd learn maybe like in the, I don't know, second month of an organic chemistry course in college. At least that's what happened to me. And I'm sure Terry probably same thing. Uh,
Yeah, yeah, definitely closer to like second, like half, more like halfway stuff that you learn in
Yeah,
college.
yeah. If I'm remembering, my first midterm in my Orgo class was like resonance, and that was it. Um, yeah, and then the second one is when like you start learning about like substitution reaction, elimination reaction, all the reactions.
Yeah, and that's mainly the substitution is like this is stuff that you mainly, especially the stuff toward the end we're going to talk about, is like mainly the stuff that you like spend probably half your orgo. Well, if you were to take just general orgo, that
Hmm.
would be like probably what you spend half of your orgo class like studying.
Yeah, it really does build up on like a lot of like where you're already learning. Like it's not like, yeah, like you can't just like learn part of it, um, or like you can't forget like what's earlier in the semester. Like understanding how resonance works is super important. Understanding how nucleophiles and electrophiles can be identified is super important for like everything else. And so yeah, that's sort of why that's our idea is like lay down the foundation. Hopefully you guys can sort of understand the foundations of all these things, and um, then substitution reactions should make a little bit more sense. And if you're ever learning stuff on your own, it should make a little bit more sense. And maybe on the test itself, like you'll have some question that will be some new concept, but like if it's using words like nucleophile or electrophile or something like that, maybe you can narrow down the answer choices to like two, right? Instead of like being a complete guess. So that's our hope. But yeah, I think we could probably get started pretty soon. Um, so yeah, Terry, you can go ahead.
Um, yeah, I guess. Do you want to wait a bit longer, or do you want to start now?
Um, I guess we could wait like a minute. But I can let people join in um, as we're talking. Oh, and for everyone, I think Terry sent out like a remind a few minutes ago. Also, so like I don't think the local like chemistry Olympiad chapter has actually opened up the registration yet, which is weird. Because the deadline is like in January. Uh, but they do have a form that lets you get email updates about the registration. So we would suggest you fill out that form that Terry sent out, and we could probably put it also in the chat. Um, it's just your email and what school you go to. Um, but
Yeah,
as soon as we have the form that you have to fill out to register officially, then we'll be sending it out in the remind and trying to get people on it.
I
Um,
just posted it in the chat. You guys
okay,
can take
good. Um, and yeah, there's no costs, by the way, for Chemistry Olympiad. You don't have to pay anything. Um, and
Yeah, and then you can also get a free $10 Amazon gift card if
yeah,
you qualify.
yeah, if you do well, then I guess you actually make money, which is cool. Um, okay, we should probably get started.
Yeah. Okay. So today we're gonna go over part two of organic chemistry. But first, we're gonna start with some like review of some of the topics we covered last week. So, yeah. So this is the first review question. Just type your answers in chat if you know.
Wait here, do you have a slide on this one with like the answer on it, or is it
Yeah.
just
I
the
think
question?
it's. I put in the next
Okay.
slide. I'm pretty sure. Okay, I don't I don't think anyone knows. We could probably just go over it. Okay, so basically the answer to this question is B, and then yeah, okay. So um if you remember from last slide, we covered the different types of isomers, and then in this question it asks what is geometric isomerism. So if you go back to the slides we covered last week, there was this like uh there was this there was this like tree diagram thing that like showed you like, what like geometric isomerism. So if you like go to answer, you know. Yeah, so geometric isomerism basically refers to cis-trans isomerism. And what cis-trans is, so first of all, cis-trans, you need to have like a double bond. And so cis means like you have your two groups on the same side. So as you can see in like the first example, like you have CHBr2, which is your first group, and then your CH3, they're on the same side. And then for trans, it means you have them on the opposite side. And so how you can determine that it's two butene is that the if you remember how the IUPAC naming guidelines that we went over last week, the E and E at the end means double bond. So and for geometric isomerism, you need a double bond so you can like cancel out you can cancel out the other two options that don't have the E and E at the end. And then you yeah, so you can cancel out the butine and then the one butine and then two butine, and then it's two because the double bond uh the double bond of cis trans is at position two. If you were to draw out your longest carbon chain and see the double bond is at position two. So that's why in this case the answer is B.
Mhm. Yeah, because in one butene, the double bond would have like two hydrogens on one side of the double bond, so there's like no different isomerism that you could come up with.
So I think this is slightly a bit easier, I think, this question. But this is just asking for just any isomers that you can think of. So if you remember, isomers are basically just you have the same formula, but you're like drawing the molecule in like different ways.
Okay, people on YouTube, I think I just lost connection. Alright, I think I just lost connection. Uh,
Yeah, you're back. You're fine now.
is my screen still sharing?
Yeah, it's still sharing.
Okay. Do you want me to go to the next
Um,
slide?
yeah, I guess we can just go over answer. So did you switch to answer tab? I think maybe your screen is frozen.
Yeah, I think, hold on. Alright. It should be updated now, hopefully.
Okay, yeah. So the answer is C, and why is because like if you draw out the C2H2Br2, you have the double bond in the middle, and then whenever you have a double bond like this at the second position, you always have to remember to you have both the cis and trans. So have you have the trans, the two BRs that are at opposite sides, and you have the cis. So the two BRs are on the same side, and then you also have this three where this like BR is like vertical. And so these are all like three completely like uh different molecules. Yeah.
Mhm. Okay. So now we're going to start talking about resonance, which you hopefully recognize from chemistry, AP chemistry or honors chemistry, because you do talk about resonance a little bit, but in organic chemistry, it's a lot more important. So an overview on resonance, what you have to understand is that electrons aren't really like you don't want to think them as like very fixed like objects in a sense, and they're sort of like I would describe them as fluid because they sort of occupy regions of space instead of like specific locations. They occupy what's called like an orbital, which is really just a mathematical function that describes the electron density um, of that region. Okay, and so down here I have sort of an example of what orbitals look like. They kind of look like balloons in a way. These little like bulbs sort of coming out. And what this basically means is that like I believe what it actually means like 95% of the time an electron is going to be like in one of these orbitals in one of these shaded regions here. Um, and so it can be pretty complicated because it has to do like quantum mechanics and stuff. And then when you're talking about like structures that have resonance structures, um, it can be sort of complicated, but we've come up with ways to describe what that is. Um, so a resonance structure really just portrays the actual electronic environment of the molecule, um, when just a single like diagram or a single drawing like this doesn't really do a good enough job of describing it. So here in this example, we have, I believe this would be like, this is basically a methyl group, and then here's a carboxylic acid. Um, And so the what you might realize is that we have here this carbon here with two oxygens attached to it, and one of those oxygens has a double bond, and the other one has a negative charge. But nothing is really telling us that we have to have this top oxygen be the one with the double bond and not the one that's off to the side. And so you could describe this overall structure here as sort of a blend of these two structures, where it's sort of like alternating the double bond. Uh, the thing about this type of like drawing for resonance structures that you want to be careful. It does not mean that there's a double bond that's sort of like flipping back and forth between the two oxygens. Um, it's not that there's two structures that it's flipping back and forth between. It's that there's one overall structure of this molecule, which is sort of a blend of these two structures. Okay, so you can sort of think it's um, imagine like the halfway point between this structure here and this structure here is sort of what the real structure of this molecule is. And so given that there's uh, it's a blend of like maybe two double bond or two single bonds here and one single bond here and a double bond here, you can think of maybe this bond as like being 1.5, which is sort of a weird thing to think about. But we call that the bond order, and the bond order would be between 1 and 2, because the two resonance structures here have 1 and 2, and so it's 1.5. The reason we care about this uh, the reason we care about this is because resonance structures help us identify regions of like high electron density and low electron density, and so respectively that would be a negative charge and a positive charge. And so if you look up here, this tells us that like both oxygens here carry a partial negative charge, as you can see here because in one resonant structure here you have this oxygen having a negative charge and the other one, the top oxygen, has a negative charge. But if you were just looking at one structure, you wouldn't know that the other oxygen can also carry a negative charge. So if you're given a drawing of a molecule, how do you know that you have all the resonance structures, or how do you draw all the resonance structures? Um, Basically, the rule here is that, or the overall process is that you're moving sort of you're showing the movement of electrons. But again, keep in mind, electrons are not really actually moving. It's sort of a blend of different resonance structures, but we can sort of show the movement of electrons as we're comparing two different resonance structures. Um, as you can see in this example here, this is the same molecule from before, just in a different format. And so what you can sort of see here is that two electrons from up here in this oxygen move down into the single bond to create then a double bond. But because that double bond is forming, we have to then move one of the pairs of electrons of this double bond here to the oxygen. Okay, and so that's how we get these two structures. The reason we can't have two double bonds in one structure, so a double bond here and a double bond here, is because that would be breaking the octet rule. So that's one of our rules for making resonance structures, is that you can't ever have more than 8 electrons on an atom, and that's just for atoms that are on the or elements that are on the first two rows of the periodic table, because you might remember like uh, elements below it you can expand the octet. And the other rule is that you can never really break a single bond. Um, so you wouldn't be able to like break or move one of the electrons or two electrons here that are making this single bond here and move it to another place, and that would result in like two separate molecules. You can't really do that either. But so those are two rules: don't break single bond and don't break the octet rule. Um, so there are sort of these key features that you can look for in a structure that sort of tells you that you can draw resonance structures with it. And so a common one is that you have two double bonds that are uh, sort of neighbors to each other, but they have one single bond as a gap in between them. So in this example here, you can see there's actually uh, uh, two of these situations happening. You have this double bond here and this double bond here, and it's separated by one single bond, and then same thing over here on the right side. Um, and another example is you have a double bond, and then you have uh, lone pairs on an atom. So in this oxygen here, you have 3 lone pairs, and they're separated also by a single bond. So that's another sort of feature that we can look for. Um, and finally, a lot of times you might have like a double bond, and then one single bond away. So again, another gap of a single bond. You have, um, actually no, this wouldn't have a. Yeah, I wrote this wrong. There shouldn't be a single bond gap. But if you have a double bond and then you have a empty orbital, so an atom that has less than an octet of electrons, you can also do resonance where the electrons from that double bond are moving to that atom to fill the octet. And so I have here an example of a structure that exhibits a lot of resonance. So you have sort of a symmetric looking thing, but you have this oxygen here with a negative charge, and that negative charge can move down here. But so that we don't break the octet rule for this carbon here, we have to then move uh, those electrons over like this, and we sort of keep moving them over until finally they end up here on this oxygen, uh, and it creates this structure here at the bottom. And you can see they sort of look pretty symmetrical to each other. Uh, and yeah, so these are two valid resonance structures. The thing is, when I did that drawing in this previous slide, we are sort of omitting a couple possible resonance structures. So what I'm showing here is sort of the intermediate steps of that process that we did. This double bond here moving, one of the electron pairs moves here, and then this also moves, and then you end up with a bunch of these formal charges here. And all these are technically legal intermediate steps, but the reason we don't really care about them and we call them not significant is because they break a lot of these rules that we care about when it comes to significant resonance structures. And so I've labeled them here as terrible. And so how do you know if a resonance structure is significant or not? Basically, you want to look at these 3 rules here. So the most important rule is your resonance structure should have the highest number of filled octets. So you should be trying to reduce the number of atoms in your structure that has less than 8 electrons. So for example, this one right here, this carbon here, by having a positive charge, it means that it would only have 6 electrons around it, and so that's pretty bad. You don't want that. Then you also want to minimize the number of formal charges in your structure overall. So if you look here at these two good structures, they only have one negative charge, and they only have one charge period. While in these two bottom ones, it actually has 5, which is an insane amount of charges. Um, and so that makes the structure really unstable. And so it rarely ever stays like this. A structure, or a structure basically a structure that looks like this isn't really important for us when it comes to predicting like reactivity and stuff because it's so unstable. And then finally, the third rule is that if you have a choice, you want your negative charges to be on more electronegative atoms, while positive charges should probably be on less electronegative atoms. And that's because if you remember the definition of electronegativity, it was sort of the likelihood or the sort of the desire of an element to hoard electrons. And so you'd imagine a negative charge would be preferred by electronegative atoms than not electronegative atoms. So if you have a piece of paper, see if you can draw all the significant resonance structures of this molecule. Um, and I'll give you guys like a minute or two, and then I'll show you the answer. And so for this one, think about the key features that we talked about, like double bonds that are one that have a single bond gap in between them, or lone pairs that are a single bond away from a double bond, for example. Um, See if you can identify those in the structure and move electrons accordingly. Okay, so I'm gonna go ahead and show the answer here. Um, so I came up here with three resonance structures that are pretty good. The ones on the, well, actually, we'll discuss each of them. So the first thing that I do here is move this electron here because we have a negative charge. That means this carbon has a lone pair. And so that lone pair moves down into this single bond and it becomes a double bond. But so that we don't break the octet rule, we want to move this double bond here, the electron pair that's on this double bond, into the carbon. So you can sort of see the lone pair is moving from this carbon here to this carbon, in a sense, is what's happening when you go from this structure here to this structure. Then finally, we can do sort of the same process, uh, continuing in the same direction. We move this lone pair down, but then we have to move this double bond, uh, the electron pair on this double bond, into the oxygen, and so we get this structure over here. And so comparing these structures here, these are all pretty valid. None of these like break, or none of these have like less than an octet in them. But I would say this one for sure is probably the best one because the negative charge is on the electronegative atom. Because oxygen, if you look at a periodic table, is more electronegative than carbon. And so in these two structures, we have the negative charge on a carbon, while here we have it on an oxygen. So this structure is more preferred. And so if you were to say something about this structure, it would be that the oxygen in this structure, in this resonance structure, exhibits a partial negative charge, which we'll see is really important for, well, for talking about nucleophiles and electrophiles. So nucleophiles and electrophiles is a category of molecules, and it's a way that we sort of describe their reactivity, like what we can predict um, that type of molecule would do. And so the two categories are dependent on the electron density of that molecule. So a nucleophile is a name we give to molecules that have regions of high electron density or high negative charge, for example. And so what they sort of want to do is they want to give away that electron density, I guess. They want to give away electrons, they want to donate electrons, and get rid of that negative charge. And they're called nucleophiles because if you think of a nucleus, it's positively charged. And so they're in a way they're attracted to positive charges because nucleophiles are negatively charged. So since opposites attract, they're sort of attracted to the nucleus of atoms is an easy way to think about it. Um, and the like we use this term called nucleophilicity to describe sort of the how good of a nucleophile is it? Like how much does it want to donate electrons? And a pretty obvious one is that something with a negative charge is more likely to want to give away its charge than something with a positive charge, for example. Because if something with a negative charge, if a molecule with a negative charge gives away a pair of electrons, it becomes neutrally charged. And a neutrally charged molecule is pretty stable. It's more stable than having a charge on it. But if a positively charged molecule gives away an electron pair, it will become even more positively charged. And so we don't chemistry doesn't really like that to have strong charges on molecules. That's pretty unstable. So yeah, that's why this would be more nucleophilic. Uh, the second thing that we're talking about here is basicity, and so yeah, nucleophiles and electrophiles and even resonance structures have a lot to do with like acid-base chemistry that you might be doing in AP chemistry, I think, next semester. Um, and uh, I won't get too much into this, but basically the likelihood of an atom or of an element to want to keep electrons makes it a worse um, nucleophile because again you see this fluorine here, which is the most electronegative element. It really likes having electrons, and so it's less likely to give them away. But meanwhile, carbon, which is not very electronegative, is probably like less stable holding that negative charge since it doesn't really like having that negative charge compared to a fluorine. And then finally, nucleophilicity increases with polarizability, and so that's just sort of a word used for describing like how much the electron cloud of an atom is sort of like malleable and can sort of change its density to create a like dipole moment inside of it. And so it has a little bit to do with like intramolecular forces, if you remember that. But so since if you look at a periodic table, the iodine is on the same column as a fluorine, but it's like much bigger. It's down like 4 rows. And so it has a much bigger electron cloud. And so it's much more polarizable. Basically, its electron density can create a dipole moment inside of it much easier, and that makes its negative charges, like the negative dense electron density region, much stronger. Then on the flip side, electrophiles are molecules with regions of low electron density, and so they have sort of a positive charge or a partial positive charge, and they want to receive electron density because again, opposites attract. So positive charged molecules want to interact with negatively charged, and they're called electrophiles because they're attracted to electrons, which are negative. And a term that's pretty important is the electrophilic center, and that's sort of the specific atom on an electrophile that has like the lowest electron density. And so here I have an example of a resonance structure that then shows us the creation of an electrophile in a sense. And so we have here this carbon that double bonded to an oxygen. And because of resonance, this double bond can move to the oxygen here pretty easily. And what comes from that is this oxygen with a negative charge and this carbon with a positive charge. And so this carbon with a positive charge is a really, really good electrophile. Um, and we're about to see how then that changes a lot of things. But you could also say this oxygen here then becomes a good nucleophile, and yeah, it could also donate us electron density elsewhere.
Yeah, so now we're gonna go over SN1 and SN2 reactions. And so, okay, so what is SN2? Well, SN2 is a type of substitution reaction, and basically what happens is you have your nucleophile, and then you have your substrate here, and then what happens is basically you want your nucleophile to replace the leaving group here, and so this negative charge from the nucleophile, it undergoes something called a backside attack, and it comes here, and then it attaches to the carbon, and then it basically kicks out this leaving group, and then so this you end up with this new product that has a nucleophile attached to carbon, and you have this negatively charged leaving group out here. Yeah. So next slide. Yeah. So okay. So this is what's called a substitution reaction, and basically you have two reactants produce two products, and then something has been switched around. So this is basically what happened in the previous slide. So it's basically AB plus C, and then you swap the B and the C, and so you now have AC plus B. So okay, so SN2 reaction is a type of substitution reaction, and um, it's a bimolecular it's a bimolecular reaction. So the rate depends on the concentrations of the two reactants. So the two reactants in this case, the rate depends on the nucleophile, and it also depends on the leaving group. And so it happens in one step where the nucleophile attacks the substrate, and then the leaving group leaves the substrate. So it all happens in one step. And so that's why it's called SN2, because it relies on it relies on the concentration of two reactants. So maybe you can go to the next slide. And so basically the mechanism, this is pretty much what I showed in the first slide, but you have the nucleophile that undergoes this attack that's called the backside attack. It attacks the substrate, and then it kicks out the leaving group. Well, first it forms this transition state where you have this nucleophile and the leaving group all attached, but this leaving group is getting kicked out, and then you end up with three. And so three is your final product where you have your nucleophile attached to your carbon and your leaving group, and then it's SN2 because because the transition state, like how fast this happens, relies on the speed of both the nucleophile and the leaving group. And so now we're going to cover SN1. So SN1 is a bit different than SN2 in that SN1 you have two different steps. So in the first step, so as you saw in like SN2, you had the nucleophile directly attack, and that attack kicked out the leaving group. But in this case, what first happens is the leaving group leaves by itself, and it forms what is called a carbocation. And so that's just a carbon with a positive charge. And so your leaving group is gone. And what happens is this positive charge is attracting this nucleophile in step 2. And then this negative charge on the nucleophile is attracted to the positive charge on the carbon. And so you end up getting an attachment. But what happens here is in SN1 is you can have like two different products because in SN2 you only get one product, because when the nucleophile attacks the substrate, it can only attack on one side. It can't attack on the side that has the leaving group. But in this case, since you don't have a leaving group, the nucleophile can attach on either sides of the carbon. So you end up getting 50% of both. And then these two molecules are different because if you remember, we covered in the previous lecture, we covered isomers, and then how this is a chiral center. So these two molecules are actually different. So you end up with 50% of each. And so you might be wondering like how exactly we determine like what happens like if we're using SN1 or SN2. So next slide. Okay, actually first we're gonna cover the different types of carbons. So you have what's known as a primary carbon. So a primary carbon is when your group is attached to is just attached to one carbon. And so that's what's called a primary. A secondary is what happens when you have a carbon attached to two carbons. So you can see here secondary. And then tertiary basically is when you have a carbon attached to three different carbons. And then quaternary is when you have like it attached to four different carbons. That's how you like name these particular carbons. And next slide. And so, okay, now we're going to move on to how you determine SN1 and SN2. So based on the knowledge in the previous slide, how you determine like the primary, secondary, and tertiary, you can determine if a reaction undergoes SN1 or SN2. So if it's tertiary, you can rule out SN2. So SN2 isn't a possibility, and so you'll most likely have SN1. And if it's a primary carbon, then you can rule out SN1 because it means it's likely SN2. And then secondary, we can't make like a determination on. We're gonna have to look at other factors. But if we look at this table here, so for the first one, the bromine, as you can see, the bromine is attached to a carbon, and then that carbon is only attached to one other carbon. So in that case, it's primary. And if it's primary, then we can rule out SN1. So it's most likely a SN2. And then if we look at the bottom, the chlorine here is attached to a carbon that is attached to two other ones, so it's a secondary. So we can't really make any determination on that. And then for the last two, both of the groups are attached to a carbon that are attached to three other carbons. So these are tertiary, so you can rule out SN2 for both of those. Okay, so now we're going to cover how you determine exactly what happens in a secondary carbon, if it's SN2 or SN1. And so first we're going to talk about charged nucleophiles. So if you have a nucleophile or a base with Na, K, and lithium, like these three are all like highly reactive, and and then they contain ionic bonds that bear a negative charge. So and then that's basically a charged nucleophile, and then basically a charged nucleophile and base tends to perform like an SN2. It also tends to perform an E2 reaction, but we're not really going to cover like E2 and E1 reactions right now. But you also have neutral nucleophiles. So what neutral nucleophiles are, there's a couple examples of neutral nucleophiles. They can be strong acids. So they could be like H2SO4, HCl, or HBr. And then these are all what you consider neutral nucleophiles. So next slide. Okay, so in this in this in this example here, you can so for the secondary now, we can we can determine based on the previous slide what it's going to be. And so as you can see in number two, the one that we had the secondary, what happens is basically because it's a charged nucleophile, um, we can rule out SN1 and we can rule SN1, and so it's most likely going to be an SN2 related reaction. And then for 1, 3, and 4, our determinations basically back up what we already saw in in one of the previous slides. Yeah. So that's just a okay. So that's just a general explanation of like how we determine like what to use SN1 or SN2. I'd recommend you guys like read further on this. It's especially asked a lot on the national exam if you're going to advance. Then you occasionally see some question on the SN1, SN2 in the local exam. But this topic is overall like really important if you plan on ever studying organic chemistry. This is just like a very basic lecture on what SN1 and SN2 is. Yeah. So now we're gonna like wrap up Orgo, and then we're just gonna go over two practice questions. So I think maybe Nuno wants to go over them with you.
Yeah, so we'll just have some practice questions reviewing stuff. So again, put your answers in the chat if you know them. Okay, so I see two people put D. Um, that is a nice idea, but it's not that. So the answer for this one is C, and so let's explain why. And so C is 3-methylhexane. So if you remember the convention for naming or the steps for naming, the first thing you want to do is list out the longest carbon chain, uh, and that will be sort of your backbone. And you build everything off of the longest carbon chain. And so looking at this molecule here, we can count 1, 2, 3, 4, 5, 6. Not 5. Like we could go if we counted down here, it would be 5, but that wouldn't be the longest carbon chain that we can come up with. So it'd be 1, 2, 3, 4, 5, 6. And so that already tells us the main word here should be hexane. And again, it's ane. We're using ane at the end because there's no double bonds or triple bonds here. So we're working with a hexane. And so, I mean, actually, I guess that would already like limit our answer to C here. But let's also talk about here the 3-methyl. Um, so 3-methyl means that there's a methyl group at the third carbon. And a methyl group is again just one carbon coming off, like one carbon substituent. So sort of a CH3. And we say it's coming off of the third carbon. And so if we actually go to the third carbon, we don't see any methyl group coming off of it. But that's because we're looking sort of from the wrong direction. When we're naming it, we also want to reduce the number on that substituent, like in our name. And so we could also think of this same molecule as going from the 6 to the 1, and we could renumber this and going 1, 2, 3, 4, 5, 6, and then you'll see that from this direction here, this methyl group that does come off of the main carbon chain is coming off of the third carbon. So that's why we name it 3-methyl. Um, this 4-ethyl pentane would be, I'm assuming what you guys were thinking was you thought 1, 2, 3, 4, 5. And then off of the fourth carbon, there's sort of these two uh, carbon groups, or I mean, these two carbons coming off, which together is an ethyl group. But even then, technically, you would want to call this a 2-ethyl pentane uh, if you were to go through this naming. But either way, it's wrong because that's not the longest carbon chain. Um, so yeah, so this is going to be 3-methylhexane. Okay, so a secondary alcohol results from the attachment of a hydroxyl group to which carbon atom? So you have four possible carbons here that you could attach an alcohol to. Which one would result in what we would call a secondary alcohol? Um, and so yeah, I'll give you guys a minute. And so what we're saying here is we want a secondary alcohol. What that means is that it's an alcohol attached to a secondary carbon. So see if you can remember what we used to determine what a primary, secondary, tertiary alcohol, or I mean tertiary carbon was, and then think which of these would be considered a secondary carbon.
Maybe you can go back to the slide about the secondary again, just real quick. Yeah.
Yeah, so look at this image, and I'm gonna go back now to the question and see if you can think which of these represents a secondary carbon. Okay, so yeah, so Liam is right. It is C3. And so again, the reason for why that is because think about each of these carbons. We don't draw the hydrogens, and you need to be comfortable not seeing the hydrogens but still realizing that they're there. So there's 3 hydrogens coming off of this carbon because we have to fill the octet rule. We have to have 4 bonds in this example, 4 bonds to each carbon, um, so that we have like sort of a valid structure. So we have 3 hydrogens coming off of here, and so going back to our image here, we would call that just a primary carbon because of this. So C1 would be a primary carbon. Then C2 here has just 1 hydrogen, and then has 3 groups coming off of it. This group, this group, and this group. And so we would call that a tertiary carbon. So still not secondary. Uh, C4 is going to be the exact same as C1. It's going to have 3 hydrogens coming off of it, and so that leaves us with C3, which sure enough has 2 carbon groups coming off of it, and 2 hydrogens, and so that's what we define as a secondary carbon. And so if we were to attach an alcohol to it like this, it would be a secondary alcohol. So yeah, that's it for this meeting, and so that's organic chemistry. Uh, it's sort of a whole new world, I'm assuming, for a lot of you that have never looked at it before. Um, I would if I were you and you wanted to study it, start with the basics and make sure you get the foundations down, understanding like isomers, configurations, and resonance before you sort of move on to the tougher stuff, which is like noticing nucleophiles and electrophiles and doing SN1, SN2 reactions. And if you want to, you could even look at some of the other reactions like elimination reactions, for example, or like carbon like rearrangement, for example. There's a lot to study. Don't feel too pressured to know everything about it, but it is sort of an interesting topic. And if you're ever going into like medicine, if you're thinking about going into medicine or becoming a doctor or something, you're definitely gonna have to know organic chemistry later on. And yeah, I don't know if Terry has anything to say.
Um, yeah, just final thoughts. I also like to point out to you guys that ACS lately like released solutions for a bunch of the previous year's local exams. So if you don't know any of the organic chemistry questions or just generally any questions you don't know, I'd recommend you like go to the past exams. So if you just type up like ACS Chemistry Olympiad and then you click that, there's like this tab for past exams. And then the now they like wrote out solutions for like I think most of the recent years. So I'd recommend you guys go check that out. And in regards to organic chemistry, yeah, I would say like what we covered is definitely like some like more advanced. We just like lightly like covered it today, but I definitely like recommend there's a couple books um that like cover organic chemistry pretty well. I guess you can like post it in the chat later if you want to like further read up on organic chemistry. It's only 5 questions on the um Olympiad, so it's not that significant. You could probably get by without studying, but it's still a pretty it's still generally a pretty important topic, especially if you advance to the national round of the Olympiad. So yeah, what I
Mhm.
want to say.
Yeah, so thank you guys for coming. This will be the last meeting of the year. We're pretty sure we don't plan on doing another one. But we will probably have one early in January next year, so that we can get one in before registration deadline. And yeah, and then hopefully we'll be able to get some practice exams in before the exam in May or in March. Sorry, I'm thinking about AP exams. But yeah, thank you guys and have a good week, okay?